Hello, everyone. We're going to go ahead and get started on section 2.2. 2.2 is on subsets and set operations. So to start off, we have our overview. We've established what a set is and how elements can be grouped together by their relationships. So now we're establishing sets that have a relationship with other sets. So it's going to start getting a little bit more complicated. So we're going to look at how sets have relationships with other sets, but also the sets that are contained within those sets to begin with. So definitely a little bit more tougher concepts from now on. But for example, we say you belong to the set of college students and you belong to the set of students taking a college math class. Those are two separate sets, and in theory, you would belong to both of them. You are a college student, you are taking a college math class. You may also be in the set of freshmen, or you can be in the set of sophomores, but you technically cannot be both. You cannot be considered a freshman and a sophomore. You are a freshman or you are a sophomore. So there's no real overlapping like how we saw when you're a college student, you can be in a college math class. Now, you may be in the set of people who like In-N-Out, and you may be in the set of people who like French fries, but you may not be in the set of people who like the French fries from In-N-Out. So we kind of see some differences here. With this last one, this is that you are involved in two sets, but you are not involved in the overlapping of those two sets. So those are some examples that relationships of what we're going to go over in this section today. So defining the complement of a set. So the first thing we're going to go over is basically what is not in a set. So first, we have to define a universal set. This is a set of all objects that are reasonable to consider in a certain situation. This is symbolized with just the letter U. So with your universal set does not contain everything in the universe. Your universal set will be something more specific, like the universal set of animals. That would be all animals that live on Earth, essentially. So in that case, that's not everything in the universe, it's just the animals in the universe. Then you just specify specific sets of animals, dogs, cats, horses, bunnies, whatever. But the universal set in that case would be animals. So it's kind of like the general category. So if you ever have to determine a universal set, that's kind of where you're going to lead. And of course, you can always make a universal set more specific. It's really based on the situation. But all right, so we have a picture here. This is called a Venn diagram. This is a very, very, very basic Venn diagram of what we're looking at right now. We'll get into harder Venn diagrams later and in the next section. So we have a Venn diagram here. Hopefully you've seen things like this before. And we say that this box, the entire box and everything in it represents the universal set. Everything in the universal set is in the box. The universal set is made of the set A. We say the set A is the circle inside. We would say that everything contained in set A would be belonging in this red circle. Everything outside of that red circle, but still within the box of the universal set, would be A complement, or the complement of A. That is everything not included in A, but still included in the universal set. So your universal set is the addition of set A and the complement of A. We have a couple relations here. We say A, the set A would be equal to the universal set minus A complement. So universal set minus everything not in A. And A complement would be the universal set minus what is in A. Everything else would be A complement. So the complement of a set A, which we symbolize as A with an apostrophe, is the set of elements in the universal set that is not in A. And in set builder notation, this would be written as A complement, so A apostrophe, is equal to curly brace X, where we're talking about X, where X is in the universal set, and X is not in set A. So those will be the properties of any element X. So that's how we write that in set builder notation. We can also describe this. We can even use roster method if it is available and convenient for us. So that's a complement of a set. So as an example, if the universal set is called U and it's Warriors, 49ers, Dodgers, Sharks, Giants, and Lakers. They're going to be sports teams in California. And A, the set A is Dodgers and Lakers. We want to know what is a complement. So our universal set is a set of sports teams in California. And we say that A is two of those sports teams, Dodgers, Lakers. So if we want to know what is a complement, we need to consider what is not in A, but still contained in the universal set. We have a diagram here, we have a little picture where it's kind of colored in. We're finding a complement. So this is the shaded area is what we're trying to find. We're saying that A is the Dodgers and the Lakers. So a complement cannot contain those two teams. It would contain every other team. So in A, we have the Dodgers and the Lakers. And everywhere else, we would have the Warriors, 49ers, Sharks, and Giants. That's what would be in a complement. Because that is what is contained within the universal set, but not contained within the set A. That is a complement. So that's an example of what we can do and how we can identify the complement. All right, moving on. We can find all subsets of a set. So the complement was what is not in a specific set. This will be sets within sets. So finding the subset of a set. As we pointed out before, you are a college student and you are a student taking a college math class. That is a relationship. You are a college student. More specifically, you are also taking a math class. So being a student taking a college math class automatically makes you a college student as well. Being a college student would be the bigger set, the outer set, and the subset of that would be a college student taking a math class. So whenever we have a smaller set contained within a larger set, we call those subsets. So a set within a set. If every element of set A is also an element of set B, then we would say A is a subset of B. So if everything is in A, everything in A is also in B. B in this case would be the larger set. It could have more elements, but as long as everything in the smaller set is also contained in the larger set, then you would say that A is a subset of B. So, for example, what we just saw before with our example here, we said the universal set was the Warriors, 49ers, Dodgers, Sharks, Giants, Lakers. The set A was Dodgers and Lakers. Dodgers and Lakers are both contained in our universal set U. That would mean that A is a subset of your universal set U. It contained 2 out of the 6 elements that were in your universal set U. So things like that. We'll look at more examples in a little bit. We do use this symbol though to designate a subset. It looks like a C that's kind of long, and then it has a line underneath. So we say that is a subset. So in this case, we would say like A is a subset of B. That's how we would write that. We can look at our picture here on the side. We see that there's one big circle and it contains 2 smaller circles. And if we look at this picture, okay, we see there's grapes, pears, apples, cherries, raspberries, strawberries, watermelon, bananas, lemons, pineapple, kiwi, blackberries. We have a lot of different kind of things going on here. If we look to kind of what is inside the biggest circle. So in the biggest circle, we have a bunch of fruit. There's a bunch of fruit there. So everything that is in the big circle, but not yet in the smaller circles, we have the green grapes, the green apple, pear, which is green, the outside of the watermelon, the green kiwi, and a blackberry. So they're not necessarily all green because the blackberry is not really green, it's more purple or so. So this on our set here, and then if we kind of look within the smaller sets, it's a lot of fruit. So we could probably say that the entire set, in this case, is the set of fruit. just a bunch of different types of fruit. So we'd say, okay, the entire set, a universal set that we're given right here, or just the larger set in general, is fruit. It's all of these fruit combined. And the smaller subsets would be the subsets of red fruit and yellow fruit. So your subset of yellow fruit, which would be lemons, bananas, and pineapple, would be a subset of the entire set, basically every single fruit that you see in the entire picture. So the smaller circles are the subsets, and the larger circle is the entire set in general. So the entire set in general in this case is fruit. And then we have red fruit would be a subset of all fruit. Yellow fruit is a subset of all the fruit as well. So that gives a picture kind of idea of what we're talking about. So continuing on with this, we say if a set A is a subset of set B and it is not equal to B, we call A a proper subset. So anything can be a subset of itself because it still contains all of the same elements as itself. So we see that that statement is a true statement. So anything is a subset of itself. So if we look over here, we have some examples. So if the set is cold and flu, so cold comma flu, a subset would be cold comma flu. It's the same elements and it's contained within the set. So anything is a subset of itself. But if they are equal, it's just a subset. If they are not equal, then we call those proper subsets. A proper subset is very similar to the symbol of a subset. It just has the kind of longer C, but it doesn't have the line underneath. If you think about it, that line underneath means can also be equal to. So, or also equal to, something along those lines. So we have proper subset, normal subset. So the line underneath indicates the or equal to part. So we can use the symbol, long C, to designate a proper subset. That would mean that A is a subset of B and they are not the same. They're not equal. So we have some facts about subsets as well. Once again, every subset is a subset of itself. A is a subset of A, B is a subset of B, X is a subset of X, etc., so on, so on. We have the empty set is a subset of every set. So the empty set is always going to be the subset of any given set that you have. We say to indicate a set is not a subset of another set, you would draw the subset symbol and a slash through it. So whatever your statement is, you would draw that symbol and slash through it to say not whatever that is, not a proper subset, not a subset, things like that. All right, saying all those things, looking back to our example kind of over here on the side, we have the set A, where A is cold and flu. So the subsets would be cold and flu, same thing, subset of itself. But the proper subsets would be the elements, the smaller elements. Since there's only 2 elements in your subset, and remember, order does not matter, so reordering it doesn't make it any different, your smaller subsets would just be each individual element. There's only 2 elements, so your proper subset would be the set of cold and also the set of flu. And lastly, the empty set. The empty set is always going to be a subset of any given set. Your subset, as a reminder, represents the set of nothing. So you have to include the set of nothing. So this is how we kind of break down subsets. You'll take each element, every combination of elements really, and break them down into their smaller pieces, their smaller subsets. So we're going to do an example. We're going to list the subsets of the following set and then label the proper subsets at the end. Our set is P is equal to Harry, Ron, and Hermione. So it's Harry Potter characters, the golden trio. So we have Harry, Ron, and Hermione. If we want to list the subsets, the first easiest subset we can think of is the set itself. Harry, Ron, Hermione. Remember, anything is a subset of itself. So the first subset we list is the exact same set we start with. Now we want to list more subsets. So we can see here that the number of elements in our original set was 3, so our first subset was 3. I now want to subtract 1. I want all the different subsets of 2. And since there's 3 of them, there's a couple different ways we can have different combinations of just 2. We can have Harry and Ron, Harry and Hermione, and Ron and Hermione. Those are the different combinations of 2. So we write those down. Harry and Ron, Harry and Hermione, Ron and Hermione. So we've listed all of our different combinations of 2. Those are all the different combinations. Now, remember, order doesn't matter. So writing Ron, comma Harry is no different than Harry, comma Ron. So always keep that in mind. The order of it doesn't really matter. You do have to have the different elements. So we've listed every combination of 2 out of the 3 elements. Now we subtract 1 again. Those were 2 elements. I'm now going down to 1 element. If I have 1 element, that basically means I'm just going to write each element that was in the original set. I'll write Harry, Ron, and Hermione, just like that. So put them in curly braces. You're just listing the 1 element. So we see at the very top, we started with the 3. There were only 3 to begin with, so there was only 1 of those. And then we went down into the 2 element subsets. Then we went down into the 1 element subsets. And lastly, the 0 element subset would be the empty set, which remember is always a subset of any set. And that's usually where you're going to finish off. You will end at the empty set. So these are all of our subsets. We can count them up. There's 1, 2, 3, 4, 5, 6, 7, 8. 8 subsets of the set of Harry, Ron, and Hermione. Last thing we want to do is label the proper subsets. We said the proper subsets were going to be the sets that were not equal to the original set. The only one that's equal to the original set is the very first subset that we wrote, the same exact set. So everything except the original subset, the very first subset, will be proper subsets. So there we have all of our subsets, including our proper subsets as well. So moving on, we can use subset notation. So here is a summary of all of our different subset notation we've learned so far. So our first symbol, see with the line underneath, we say that is the subset symbol. It indicates a subset, meaning each element in the first set is also an element in the second set, or another set. So we have a couple sets here on the side, and we have some examples. We say C is a subset of D. C is the set of 4, 5, and 6, and D is also the subset of, or set of 4, 5, and 6. Since we say that all of the values in one set, if they are the same in another, they are considered subsets. So C is considered a subset of D. Then we have not a subset, meaning that the elements in one set are not going to be in the second. So for example, A is not a subset of C. A is the set of 1, 2, and C is the set of 4, 5, and 6. 1 and 2 are not found in the set of 4, 5, and 6, so therefore A is not a subset of C. Then we have proper subset. So remember, a proper subset is a subset that is not equal to the original set. So it indicates a proper subset where one set is a subset of another. They're not equal, they're not the same. So for example, A is a proper subset of B. B is the set of 1, 2, and 3. A is a set of 1, 2. B has an extra element, 3, but 1 and 2 are still contained within B, which is the set A. So 1 and 2 is a proper subset of 1, 2, and 3. It is a subset that is smaller, not the original of the other set. And lastly, we have not a proper subset, where one set is the subset of the other, but they're going to be equal. So C is not a proper subset of D. They are the same set. They are equal. So that is not a proper subset. One important thing to note when it comes to proper subsets is that all proper subsets are subsets. They are general subsets. They are a more specific type of subsets. Not all subsets can be proper subsets, but all proper subsets are subsets. Just said the word subset quite a few times, but hopefully you get the idea. So proper subsets are just a more specific type of a general subset. So, all right, another example. Decide if the statements below are true or false. So A, we have the set Lake Erie, Lake Huron. We're saying is not a proper subset of the set of Great Lakes. The Great Lakes are the set of 5 lakes in America, and also bordering Canada as well. So the set of Great Lakes, there are 5 Great Lakes. There's Lake Erie, Lake Huron, Lake Ontario, Lake Superior, and Lake Michigan. So Lake Erie and Lake Huron are included in the set of Great Lakes. They're not the same, doesn't have all 5 elements, it's just 2 of the 5. It means it is a proper subset. So that statement would be false. It's a false statement. Lake Erie and Lake Huron are proper subsets of the set of the Great Lakes. Then we have B. We have U, the set of UVWX is a subset of XWU. Now remember, we say if something is a subset, we're really stating that the first set is a smaller version or smaller subset of the second set. And if we look at this, this is the first set. U, V, W, and X is the first set, and X, W, U is the second set. Well, X and W and U are contained in both sets, but the first set has the element V as well. So if our very first set has an extra element, that is not contained in the second set. U, V, W, and X would not be a subset of X, W, U. The second set has to contain everything the first set does. Potentially more, but it does have to contain everything in the first set. So that is also a false statement. What would be a true statement is saying that X, W, U is a subset of U, V, W, X. That would be true. But in order for that to be true, you would need to switch their positions. XWU would need to be first, and UVWX would need to be second. So both of those statements ended up being false. So we're going to do a longer example together. We're going to list all of the subsets of the set B, which is AT&T, T-Mobile, Verizon, and Sprint. Then at the end, we'll label which ones are the proper subsets as well. So this is a slightly larger set. On our last example, we looked at a set of 3 elements. This is a set of 4 elements. And if we remember from our set with 3 elements, we ended up in total having 8 subsets. So let's see how many subsets we end up when the number becomes 4 elements. Shouldn't be that different, right? All right. So we're going to list out all of the subsets of our set B, and we'll label which ones are proper subsets as well. Now, always a good place to start is just rewriting the original set. We say that a set is always a subset of itself. That's the first one. So we'll go ahead and write our first one in here. AT&T, T-Mobile, Verizon, and Sprint. This is our very first set. And you know what? Let's just go ahead and label it. So we'll label that set number 1, subset number 1. So now we want to move into the smaller subsets. And like we did before, our very first subset here is 4 elements. So the next subsets we're going to list, let's go ahead and list the combination of the 3 subsets. So we'll do every variation of 3. So let's go ahead, do AT&T, T-Mobile, and Verizon. Put little dots above it so we can kind of remember which ones we're picking. So we'll have AT&T, T-Mobile, Verizon. All right, cool. That was one. So now we want to do another combination of 3. Another combination of 3 can be AT&T, T-Mobile, and Sprint. So we're leaving out Verizon this time, having Sprint instead. AT&T, T-Mobile, Sprint. All right, let's do another one. So this time we can do AT&T, Verizon, and Sprint. So we're skipping over T-Mobile this time. So AT&T, Verizon, Sprint. All right. Now there should just be one combination left. We should just be leaving out AT&T at this point. So we have T-Mobile, Verizon, and Sprint. And let's label these ones too. So this was 2, 3, 4, and 5. Okay, so those were all the different combinations of 3. And once again, just like before, we're going to go back down into 2. So we went from 4 to 3, now we're going from 3 to 2. So now I want all the different combinations of the 2 elements out of 4. So we'll start up again. Let's go AT&T and T-Mobile. Scoot this down a little. So there's 2. We could do the last 2, Verizon and Sprint. Let's do the first and the third. We can do AT&T and Verizon. We can do the second and the fourth. There's always going to be quite a few combinations once you start having more elements within your subsets here. So we've run out of room a little bit, so let's go kind of off to the side. So we're continuing over here. We'll have T-Mobile, Sprint, we're running out of colors here. Let's go with like an orange. There we go. So now we can go ahead and let's do first and last. So AT&T and Sprint. And the middle 2, T-Mobile and Sprint. Let's pick a new color. Struggling with a new color now. We'll go with this color too. Maybe like that color. There we go. So T-Mobile and Verizon, center ones. Whew. Those should be all the different combinations of 2. So we'll label these now as well. So 6, 7, 8, 9, 10, 11. So those are all the different combinations of 2. We had AT&T and T-Mobile, Verizon and Sprint, AT&T and Verizon, T-Mobile and Sprint, AT&T and Sprint, T-Mobile and Verizon. So we had quite a few different ones there. So now we listed all the different combinations of 2, subtract 1 again. We're going to do all the different combinations of 1. Thankfully, it's only 4 elements at all, so it'll be the 4 separate elements just by themselves in a set. So we don't necessarily need to draw any other colors at this point. We can see which one is which in there. So we can have the set AT&T, T-Mobile, Verizon, and Sprint. Those are all of them by themselves. So all of our subsets of 1 element. Label those. And lastly, we said an empty set is always a subset of any set. So our last subset would be the empty set. 16 subsets in total. So we saw before that a set with 3 elements had 8 subsets in total. Just by adding 1 extra element, that became 16. It doubled. When we had 2 elements, that would end up being 4 subsets. We go from 4 to 8 to 16. We might be able to assume what's going on. But let's go ahead and go back on over to our notes to finish this up. All right, so we finished up this example. Now we can talk about finding the number of subsets for a set. So like we saw before, a set of 2 elements would end up having 4 subsets. A set of 3 elements would end up having 8 subsets. A set of 4 elements would end up having 16 subsets. And we see the pattern. So also, thing to remember, a set with 1 element has 2 subsets. It would be itself and the empty set. So we see this increasing. We can use our deductive reasoning skills that we learned about in chapter 1 to figure out how many subsets would belong to a finite set. An infinite set would have infinite subsets. But so we have our number of elements. If we have 0 elements, that is the empty set, and it's always a subset of itself. So that's 1 subset. 1 element would have 2 subsets, 2 elements have 4 subsets, 3 elements have 8 subsets, 4 elements have 16 subsets, 5 elements would have 32 subsets, and it just continues on in that pattern. We say the number of subsets for a finite set, because typically we only find subsets for finite sets. We'd say if a finite set has n elements, then the set itself would have 2 to the power of n subsets. So for example, 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 equals 8. 2 to the power of 4 equals 16. And 2 to the power of 5 equals 32. And it continues on in that way. And we also have proper subsets. We said the proper subset would be just everything except the set or the subset of itself. So proper subsets would be 2 to the power of n minus 1. Always just 1 subset of itself. So now we can find the number of subsets for a finite set without actually finding all of those subsets and counting them. We know how many subsets it would potentially have. And this rate that we're increasing at is called an exponential rate or a doubling rate because we see the numbers are doubling. 2 plus 2 is 4, 4 plus 4 is 8, 8 plus 8 is 16, 16 plus 16 is 32. So we see the numbers are doubling exponentially, kind of in the rate of bunnies as well. So we are now able to find the number of subsets a set would have without finding all of them and counting. So for example, how many subsets and proper subsets does each set have? Part A, we have the set G. G is the set tree, shrub, flower, plant, branch, grass. So it's got quite a few elements in there. We can count those up. Tree, shrub, flower, plant, branch, grass. That's 6 elements. So if we want to know how many subsets it would have, that would be 2 to the power of 6. So you would calculate 2 to the power of 6. You can do this on your calculator. Now, one important note about a calculator is how to find that whole power of button. Typically, your power of button will be like a little caret, like a caret button. So you see that button would be the exponent. So you write 2, use that button to the power of 6. It should equal 64. So 2 to the power of 6 equals 64 using the caret button right there. This is for a TI-83. A TI calculator will be extremely similar. Any other calculator, you may just have to look a little harder for that button. Definitely, if you don't know where it is or can't find it, I highly recommend always Googling it, looking it up. So there would be 64 subsets. Minus 1 would make it 63 proper subsets. So that's how we can calculate how many subsets are going to be in a specific set. So for D, or for part B, we have the set D. D is the set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They already counted, it's 10 elements. So we have 10 elements there. In that case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 elements. That means you would have the subsets equal to 2 to the power of 10. So we go in our calculators, we calculate out 2 to the power of 10, and 2 to the power of 10 should end up being 1,024. So it means we have 1,024 subsets minus 1 proper subset makes it 1,023 proper subsets. So that's how we'll calculate how many subsets we have in a given set of any number of elements. And this way, that would be a whole lot of subsets to try to write out ourselves. We definitely don't want to do that. So this way we can just calculate how many there should be in theory. Now, this will help us a lot. If it ever comes down to really listing out subsets now, we can find out how many we needed to have. When it came to finding all the subsets of our 4-element set that we did together, knowing this fact, we know there should be 16 subsets. If I didn't know that, I would kind of just be guessing or just working my way through it, not really knowing when the end goal is. I knew it would be 16 because I know this fact. So I was able to show you how we end up getting 16. But now you can use this fact when you're finding subsets. You can see how many subsets should I have. And then you can find those subsets from then on. So there we go. Calculate how many subsets a set will have. So that was a lot of different calculations with like sets within sets. Now we're going to look at the relationship between 2 separate sets. So we're moving into having separate sets and their relationships. So we're going to find intersections, unions, and differences of sets. So all these things are different relationships. We can combine sets using set operations, rules for combining 2 or more sets in order to form a new set. The set operations are intersections, unions, and differences. We have some pictures here. We see the intersection is this top one. You have 2 sets, A and B. And we see that there is a place where they overlap and there are elements in that overlapping section. That means those elements are found in set A and also in set B. They're overlapping the set or the elements that are in both sets is called the intersection. Then below we have the union. We have set A and set B, and everything is colored in. Everything in A, everything in B, and everything in both. We call that the union, or everything in all, A, B, and both. So those are the 2 main relationships we're going to look at. We'll look at differences as well. So starting off with the intersection. So the intersection of 2 sets, A and B, which we symbolize by writing A, B with like an upside down U in between. We say that's the intersection symbol. We say that is a set of all elements that are in both sets. Both. It's the overlapping part. It's not A and B and both because that's the union. The intersection is in both. What is in both sets? If we look at this picture here, any number in the circle is considered an element of the set. So if we look at this picture, we would say the set A contains 10, 12, 14, and 15. They're still within the red circle. Now for the blue circle, we have B. So everything in set B would be 13, 16, 17, 14, and 15. It's still within the blue circle. So we see that within those two sets, they share the elements 14 and 15. Those are the elements found in both of the sets. That would be the intersection. It is found in both of them, the singular elements found in both. In set builder notation, we write this as A intersect B is equal to X, some element X, where X is in A and also in B. So it has to be both, and it's just both. So when the intersection of two sets results in an empty set that is possible, we call those sets disjoint. If we look at the image below, there is no overlapping section. That means that they do not share any elements. That would be the empty set. The way that we would write no elements is the empty set. So if you take the intersection of two sets and the result is the empty set, that is being called disjoint. So they're called disjoint if they do not have any overlapping or shared elements. A very common example would be the intersection of even and odd natural numbers. For natural numbers, those are 1, 2, 3, 4, 5. Continuing on, doesn't include negative numbers and doesn't include 0. 0, always an iffy one, but if we exclude the 0 by saying natural numbers, then there are no numbers that are both even and odd. That would be disjoint if we took the intersection of the two sets. They don't share any elements. Numbers are either even or they're odd. So those would be disjoint. That's a very common example. Moving on, we can look at unions and differences. The union of two sets A and B, which we symbolize as A union B, where the union looks like a big U. That is the set of all elements that are in set A or set B or both. In other words, kind of in all. So it's everything in A, everything in B, and everything in both. So it's kind of the sum of it all. In set builder notation, we write this as A union B is equal to X, where X is in A, and X is in B, and X is also in both. So here is the correct version in set builder notation. We have A union B is X, where X is in A, so contained in set A, and X is contained in set B, and X is contained in both. Now remember, the intersection indicates the both part. So we would write A intersect B to represent both mathematically. So X is all in set A and in set B and in both using the intersection. So the difference or set subtraction, we say the difference of set A and set B is the set of elements that are in set A that are not in set B. So you always kind of base it on your original set, the first set you're mentioning. So in set builder notation, this looks more like A minus B would be elements of A, so X, where X is in A, but X is not in B. So how we would actually look at this is we're saying that I have my set A. Typically, not always, we will have an overlapping part where some elements in A are also shared in B. You would be subtracting those values, those elements. So you take away the elements that are also in B. So A minus B, the difference between these two sets, would be what is in set A and not in set B at all. So you kind of end up with this shape here. So you're excluding what is in the both category, just what is in A. And that's how we usually read set subtraction. It's always going to be your first set and subtracting whatever is contained in both. If there's something in set B that is not even in both, that is not even considered. It is everything in set A minus the overlapping part. Ignore everything else in set B. So it's always, you start with your very first set, whatever's labeled first, and you're subtracting the both from the original set. So that's how set subtraction works. Having these diagrams can be very useful when you go and do problems like these and give you a really visual example of kind of what's going on. So we're going to do an example. So let's say we have set A and B. Set A is the set of nausea, dry mouth, and fever. The set B is the set of weight loss, fever, and nausea. We're going to do a couple different set operations. A, we're going to take the intersection, A intersect B. B will do A union B. And C will do A minus B, so set subtraction. So starting with A intersect B. Now remember, we're talking about what elements are in both of the sets. So if we look at A, nausea, dry mouth, fever. We look at B, weight loss, fever, nausea. So we can look first, nausea is in both sets A and set B. So that is an element that they share, it overlaps. We can look A, dry mouth. Dry mouth is in A, but it is not in B. So those are not shared. They do not overlap. That's not in the intersection. And lastly, we have fever. Fever is in set A and also in set B. That is part of the intersection. So looking at our two sets, our sets share the elements nausea and fever. So A intersect B would be the set of fever and nausea. Nausea and fever, remember, order doesn't matter. That would be our intersection. It is the elements that they share with each other. Now moving on to the union. We have A union B. We're talking about the union, so we're saying everything in A and everything in B and everything in both. We know that everything in both part, it's fever and nausea, that is included in both of them, and everything else in A. Well, the only thing left in A was dry mouth, and the only thing left in B was weight loss. So if we consider everything in both sets, that would be nausea, fever, dry mouth, and weight loss. There you go. So it'd be the elements in everything. You will never repeat elements either. Remember, your elements in a set need to be unique. You can't be repeating the same numbers. Then lastly, we have C, A minus B. So now we have that set difference. So when we say A minus B, basically we're starting at A. A is nausea, dry mouth, fever. I am subtracting what they share. We said that they shared fever and nausea. So I will subtract fever and nausea from my set A. And when I do that, the only thing I'll have left is dry mouth. That would be our answer. So set subtraction is always, you start with the first set and you take away what they share. Set B also contained weight loss, but that was not part of the question. It was everything in A minus what is shared, minus what is also in B. So you always start with the first, subtract the shared. So A minus B leaves us with dry mouth. All right, and those are some more basic examples. Let's go ahead and do a more difficult one. So now we're going to work on having more difficult problems. We're also bringing in the complement, which is what we went over in the very beginning of our lecture here. So we have some sets. A is the set Cleveland, Indianapolis, Chicago, Des Moines, Detroit. B is the set New York, Los Angeles, Chicago, Detroit. And C is Seattle, Los Angeles, and San Diego. So what we're going to do is for part A, we're going to find A union B complement. The first thing we'll do is find A union B, and then take the complement. For B, we have A union B intersect C complement. So we're definitely going to have to do quite a few things here. So let's go ahead and go on over to our notes. All right, so for this example, we need to find quite a few things. We have 3 sets. Now, we said before, we're going to start using complement. Whenever you use complement, you need to know what your universal set is going to be. So in this case, we have set A and B and C, and we don't necessarily have a universal set. If we look at these sets, they're all cities. My universal set could be just all of the cities. Or we can say, in this case, for our purposes, we can go ahead, we can use all of them. So if we use all of them currently, our universal set will be Cleveland, Indianapolis, Chicago, Des Moines, Detroit, New York, Los Angeles, Seattle, and San Diego. So those are contained in all sets A, B, and C. Now, for fun and for our problem purposes, we're gonna go ahead and add just 2 more cities. We'll go ahead and we're gonna add Phoenix and Boston as well. So this is the universal set that we're going to be working with. This wasn't originally stated in our question. If you are not given a universal set or even indicated to what a universal set could be, you could use every element that is just given to you in total. Now for this one, for our problem, we're going to practice using a couple extra elements in our universal set. And typically, your universal set will be given to you in your problem, or it would have a very clear statement as to what your universal set would be. So for this one, this is the universal set that we're working with. This is the one that I'm going to give you. It will be given to you or very explicitly expressed. All right. So starting off with part A union B complement. So what we're looking at here is A union B, and then everything that is not in that. So everything within the universal set that is not in A union B. First, we need to know what's A union B. So we're going to figure out what is A union B. So starting off, we have A union B. It's going to be everything that is in both sets. A is the bigger set, it's what we start with. So we'll just list everything in A, because remember, it's everything in A and everything in B and everything in both. So we'll list everything in A first, and then we'll kind of just go from there. So starting off, A union B would be Cleveland, Indianapolis, Chicago, Des Moines, Detroit. Then we go into B. So what is in B? And then what is also in both? We can look to B. We see B as New York, Los Angeles, Chicago, Detroit. Chicago and Detroit are already in set A. We don't need to write those again. So we'll finish off with New York and Los Angeles. All right. So A union B, everything in A and everything in B and everything in both. So A union B would be Cleveland, Indianapolis, Chicago, Des Moines, Detroit, New York, Los Angeles. Everything in A, and basically everything else in B. And then we see Chicago and Detroit, those are shared. Those are the ones that are in both. So we found A union B. A union B complement is going to be everything else except what's in A union B. Everything else in the universal set U, which is what we wrote out there. we said U was Cleveland, Indianapolis, Chicago, Des Moines, Detroit, New York, Los Angeles, Seattle, San Diego, Phoenix, Boston. It will have everything except what's in A union B. So A union B complement. So let's just go ahead. We'll go over to our universal set. We're going to figure out what is in the universal set that's also in A union B. It will be everything else except those. So we'll go ahead. Our very first element in A union B was Cleveland. Well, yep, Cleveland is definitely in the set there. Oop, that was too big. There we go. Okay, Cleveland is in the set, so it's not going to be included in our complement. Then we have Indianapolis. Okay, Indianapolis is there. Then we have Chicago. Then we have Des Moines. And then we have Detroit. Then we have New York. And then we have Los Angeles. That's where it ends. A union B contained all of those cities, and it does not contain Seattle, San Diego, Phoenix, or Boston. So A union B complement would be everything left over. Seattle, San Diego, Phoenix, and Boston. So that's what we'll write. So A union B complement becomes Seattle, San Diego, Phoenix, Boston. Boston. There we go. That would be your answer. Question was A union B complement. So to start off that question first, we had to find A union B. Then we went on into what is A union B complement. What is not in A union B, but is still within the universal set. So there would be our answer. Now we can go on to part B. Part B is A union B intersect C complement. So in this one, we're actually still using A union B. So we can go ahead and copy that set for part B, but then we'll also have to figure out what's going to be C complement as well. So let's go ahead and write those. All right, so for part B, we've copied A union B. So we know it's still what's in A union B. But now we want to find C complement. We need to figure out what C complement actually is. We're going to base that off of what's in C. So let's go ahead. We'll write C complement. And then we'll go back up to the top. We said C was Seattle, Los Angeles, San Diego. C complement is going to be everything in the universal set except for what is in C. So we'll figure out what is in C that is in the universal set. Seattle, Los Angeles, San Diego. So we can't have Seattle, we can't have San Diego, we can't have Los Angeles. That means everything in C complement is everything else. That means C complement is going to be Cleveland, Indianapolis, Chicago, Des Moines, Detroit, New York, Phoenix, and Boston. Quite the list. So let's go ahead and write that. All right, so C complement, we said, was Cleveland, Indianapolis, Chicago, Des Moines, Detroit, New York, Phoenix, and Boston. So now we're finding their intersection. We're finding what is in both. So this intersection right here is the both, where the union is the all. So we found A union B, which we've done from the part before. Now we found C complement. So we're finding what is in both of the sets. What elements are they going to share? So let's go ahead and use our highlighter and just kind of go element by element and figure out if they share it. So starting with Cleveland. Cleveland is in both. So Cleveland would definitely be in the intersection. Then we see Indianapolis is in both. Chicago is in both. Des Moines is in both. Detroit is in both. New York is in both. Los Angeles is not in C complement. Phoenix is not in A union B. And Boston is not in A union B. So only the ones that were highlighted are actually the intersection. What is in both? We'll copy those down to finish this up. A union B intersect C complement. It's everything we highlighted. Cleveland, Indianapolis, Chicago, Des Moines, Detroit, and New York. And that would be our answer. One thing that we kind of jumped into that wasn't exactly explained was the beginning, the A union B. We notice it has parentheses. That means you need to find A union B first, and then do everything else. If you didn't have those parentheses, it would be A union B intersect C complement. If there's no parentheses, in theory, you could go from beginning to end, or you could pick which ones you wanted to do first. So the parentheses are telling us this is what you need to find first, then do everything else. So those parentheses around A union B told us we definitely needed to have A union B first, and then we could take the intersection with C complement. So, all right, that wraps up our example there. So let's go back on over to our lecture. All right, this was our last example, and that wraps up section 2.2. So in summary, in section 2.2, we learned how to define the complement of a set, find all the subsets of a set, use subset notation, find the number of subsets for a set, and find intersections, unions, and differences of sets. So, all right, that wraps up section 2.2, and I'll see you in the next one.